1.4. Inverses, algebraic properties of matrices. So in algebra, what we do is whenever we introduce some object, we define operations on that. And then when we define operations on that, we look at the properties of those operations. So the first thing that you learned was real numbers. And then you learned how to add them up, how to subtract them, how to multiply them. Then you learned about the properties of these operations. So what are the properties of multiplication? What are the properties of addition or subtraction? So there you learned about associative property of real numbers. Like, for example, if you have A, B, C, this is not ambiguous. You can just do A, B first and then multiply that by C, or you can do A times B, C. So it doesn't matter which two you associate first. You can associate this two first, or you can associate this two first. So you have the associative property for real multiplication. You have the same property for real addition. If you have A plus B plus C, this is not at all ambiguous, because if you associate the A and the B first, or if you associate the B and the C first, you're going to get the same answer. So these two are called associative properties. Commutative property, A plus B is B plus A. That means it doesn't matter in which order you add up real numbers. So I'm talking about these properties. So if we, and about other mathematical objects, it's the same story. We learned about matrices, then we learned about operations on matrices. Now it's time to look at the properties of these operations. Later on, we're going to learn about vectors. We will learn how to do operations on vectors, how to add them up, subtract them, multiply them. And then we'll look at the properties of these operations. Same for functions. So if you remember in algebra, you learned about functions, then you learned how to create new functions from old functions by adding them up, subtracting them, multiply them, dividing them. And you learned about the properties. So we are there for matrices. We're going to look at the properties. So one property that matrices do not have is commutative property for multiplication. That is, A times B is not generally equal B times A for matrices. And here you have examples. Imagine A is a matrix that is 2 by 3, and B is a matrix that is 3 by 4. Then you can see that since the dimensions are 2 by 3 and then 3 by 4, the inner dimensions are the same. So AB would be defined and it would be 2 by 4. However, BA would be undefined, because if I write these matrices in this order, first I put B, so B is going to be 3 by 4, and A is 2 by 3. You look at the inner dimensions, 4 and 2 are not the same. That means BA would be undefined. So this is an example of a situation where in one way, in a certain order, A, then B, the multiplication is defined, but in the reverse order, BA, the multiplication is even undefined. So that was one example. Now, what if both of them are defined? So imagine you have a situation that A is 2 by 3 and B is 3 by 2. So in this case, in any order, the result is going to be defined. AB would be 2 by 2. BA would also be defined, but BA is going to be 3 by 3. Because look, if I put the B and A, 3 by 2, and then 2 by 3, the inner dimensions are the same, and the product BA is going to be 3 by 3. So again, it would be impossible for these two matrices to be the same, because one of them is 2 by 2, the other one is 3 by 3. So that's another example, that's another counterexample showing that AB and BA are not generally the same. And there is even a third one. You may ask, what if these are square matrices? What if A is 2 by 2 and B is also 2 by 2, so that AB is defined and it's 2 by 2, and BA is also defined and it's 2 by 2. What about that? Isn't that situation A times B the same as B times A? There's also a counterexample for that here. So imagine A is this matrix, B is this one. You are free to multiply them. You will see that AB is going to be this. BA is going to be something totally different. Not even one entry of these two matrices are the same. So, big takeaway from this example that I gave you, don't forget this, for matrices, AB is generally not equal BA. Apart from this property, which is called the commutative property of multiplication, which does not work for matrices, many other properties actually work. So here is a list of all those properties that work. The properties of matrix arithmetic, assuming that the sizes of the matrices are such that the indicated operations can be performed, we have all these rules. Okay, so let's take a look at these rules. A plus B is B plus A. This one is called commutative property of addition. A plus B plus C would be the same as A plus B plus C. Associative property of addition. A times BC is the same as AB times C. So as long as you keep the order the same, A, then B, then C. It doesn't matter whether you multiply BC first or you multiply AB first. You have the associative property of multiplication. Distributive property from the left, distributive property from the right. It works with addition, with subtraction. Distributive property if you have a real number. So if you have a scalar like 2 and you want to multiply that by A plus B, that can also be distributed from either left or right, and also with addition or subtraction. Same is true if you have two real numbers, let's say 2 plus 3, you multiply that by the matrix A, you can distribute that. So you get 2A plus 3A. So in a situation like this, you would be able to factor out the A to the left, and you add the 2 and 3, this would simply be 5A. With subtraction, and also the associative property for two scalars and one matrix. So if you have two scalars, for example, you have, let's say, the numbers A and B, and you have a matrix, let's say, D. Yeah? So you can do this operation first, or you can do this operation first. It doesn't matter. You're going to get the same answer. And finally, the last one. Imagine you have 2 times B times C. This would be the same as 2B times C. This would be the same as B times 2C. So the scalar can be multiplied by B or can be multiplied by C, or you can do the matrix multiplication first and then do the scalar multiplication. All these properties can be proved using the definition. So here you have the proof for some of them. You have the proof for A, you have the proof for B, for D. And let's take a look at the proof for D. Which one is D? D is the one about the distributive property. So we want to prove that A times B plus C is equal AB plus AC for matrices. Any questions so far? So the proofs in linear algebra are very interesting. Actually, I believe that the proofs are much more interesting than the calculations. The calculations are actually tedious, but the proofs are very interesting. But I also understand that many of you guys are not into proofs. And this course also, I'm not going to give you a lot of proofs in the test, but you may get a couple. So in order to prove something like that, we have to begin with the most general form of the matrices. So we only define the A, the B, and the C so that these operations are defined, are possible. So assume that A is a matrix which is M by R. Then B is a matrix that is R by N. It has to be R by N so that the inner dimensions are the same, and then AB is defined. But M does not have to be the same as N. This could be two different numbers. C must also be R by N, because if C and B are not the same size, then this addition here would not be defined. So that's the most general form you can define these two matrices, these three matrices. When you are trying to show that two matrices are the same, so here we have one matrix on the left and we have another matrix on the right. When you're trying to show that these two matrices are the same, you have two steps. Step one, show that their sizes are the same. Step two, show that every entry are also the same. These are the two steps in proving the equality of two matrices. So let's see. B plus C would be R by N. Then A times B plus C would be, so if I just do A, which is M by R, times something that is R by N, the result is going to be M by N. M by N. So far we learned that on the left, the size is M by N. What about the other side? AB would be M by N. AC would also be defined, and it would be M by N. So AB plus AC would also be M by N. So we prove that the right side is also M by N. So far we did step one. We proved that the left side and the right side are the same size. Are we good so far? No questions? Okay. Now the next step is to prove that the entry on the ith row and jth column of the matrix on the left is the same as the entry on the ith row and jth column of the matrix on the right. So I want to show that the entry on the ith row and jth column of the matrix on the left is the same as the entry on the ith row and the jth column of the matrix on the right. So that's the next step. And in order to prove this, I have to start here, use the definitions, and try to end up here. So that's the goal. I have to start here and then use the definitions that we learned about how to multiply matrices, how to add them up, and then work my way using algebra to reach the other side. Okay, so let's do that. A times B plus C ij. Okay, you can see that this is a multiplication. This is a multiplication and the shared dimension is R. So according to the definition, this is going to be sigma K from 1 to R A I K times B plus C K J. So this is the definition that we learned for matrix multiplication in the previous section. I'm going to remind you that definition. So this is something that you learned in 103, 1.3. So if we said that if A is, let's say, M by R and B is R by N, then AB would be defined and it will be M by N. And the definition for the entry on the ith row and jth column of the product matrix is going to be sigma K from 1 to R, where R is this shared dimension, the number of columns of A, which is also the same as the number of rows of B. A I K times B K J. So that was the definition for matrix multiplication. So when you compare this one and this one, the only thing that I'm doing here is that the B has been replaced with B plus C. That's the only difference. Here I had only B, but now I am multiplying matrix A by the entries of matrix A plus B, B plus C. So that's why I have B plus C here. Is that clear? So this step is just due to the definition of matrix multiplication. Now, next step. I'm going to use the definition of addition. So K from 1 to R, A, I, K, no change there. There is a definition for this as well. This is defined to be the entry on the kth row and jth column of B plus the entry on the kth row and jth column of C. Because when you want to add up two matrices, you just add up the corresponding entries. So this would be the entry on the ith row and jth, on the kth row and jth column of B, plus the same entry, the same position entry from matrix C. Next step, now we're not dealing with matrices anymore. Now we're dealing with just numbers. These are entries. So now I can use the properties of real multiplication. We know that we have the distributive property when we are dealing with real numbers. So I can multiply this by this and this by this. I get sigma K from 1 to R A I K times B K J plus A I K C K J. Next step, I'm going to use the properties of sigma. We know that, so I've written it here. Sigma AI plus BI is sigma AI plus sigma BI. Basically, what we have here is the commutative property of addition. So if you have, let's say, A1 plus B1 plus A2 plus B2 plus A3 plus B3, you can also first add up all the A's and then add up all the B's and then add up the 2. So that means I can distribute this sigma. I can write that as sigma K from 1 to R AIK BKJ plus sigma K from 1 to R AIK CKJ. Now I can use this definition here again and see that what we have here is simply ABIJ. And what we have here, so this one is ABIJ, and this other one here is ACIJ. So I began here, I ended up here. I showed that the entry on the ith row and jth column of this matrix is the same as the entry on the ith row and jth column of this matrix. There is one last step. This is AB plus AC JIJ. And here I'm using the definition of addition from here, from last step. I'm using the definition of addition. So I have written this proof in the notes here for you, and then above each equality, you have the reason for that equality. So the first equality here, that's the definition of multiplication. This one here is the definition of addition. This one is the distributive property of real numbers. This one is one of the properties of sigma. This one here is the definition of multiplication. And the last one is the definition of matrix addition. So each one of these properties can be proved using the same manner. Any questions? Some of them, some of these properties, you're supposed to prove as exercises. So if you look at the list of the exercises in the book, is asking you for, I don't know, theorem number, you have to prove part B, C, something like that. So for some of them, you're supposed to be able to prove them as exercise. Okay, so example 2, associative law of matrix multiplication. So we learned that A, B, C. This is not ambiguous. I don't need to put braces because with matrices, A, B times C and A times BC are the same. So this is called the associative property of matrix multiplication. The proof is very interesting, but I'm not going to show you the proof. The only thing that I want to show you here is, let's just do an example and see whether it actually works for this particular example. When A is a 3 by 2 matrix, B is 2 by 2, and C is 2 by 2. So if I multiply A and B, and then multiply the result by C, or if I multiply B and C first, and then do A times BC, do I get the same answer? And you can check that. You'll get the same answer. Any questions?
Sir, can you repeat what will have the same answer?
If you multiply these two, A and B, and then multiply the result by C in this order. That's one way of doing it. The other way of doing it is do the B times C first. You get BC, this matrix here. And then multiply A by the result in this order. You would get the same answer. Make sense?
Yeah, thank you.
Sure. If I give you three numbers, like for example, 2 times 3 times 5, Yes, it is not ambiguous. There is no confusion here because you can do this first. That would be 6 times 5, giving you 30. Another student may do this. I'm going to do this one first. That would be 2 times 15. That is also 30. Yes. Same story for matrices. You can associate A and B, or you can associate B and C. It doesn't matter what you do. You're going to get the same answer. And here's an example for that. You're good? Okay. So, you know that among real numbers, there are some numbers that are special. Yes. So, like the number 0 is a special number. The number 1 is a special number. There are also 2 other special numbers, pi and e, which you have definitely seen in calculus. But these 2, the 0 and the 1, they are special. Because these are called the identities, or the neutral members. 0 is the neutral member when it comes to addition. That is, if you have any number and you add 0 to that, or if you have 0 plus any number, you're going to get the same number. So this one is the neutral number for addition. 1 is the neutral number for multiplication. That is, if you multiply 1 by any number in any order, you're going to get the same number. So that makes 0 and 1 special. Among matrices, we have some members that can play the role of 0 and the 1. So the matrix that plays the role of the 0 is called the 0 matrix. So for example, this matrix, a matrix where all the entries are zeros. That plays the role of the 0 among all the class of 2 by 3 matrices. So think of all the 2 by 3 matrices as a class of matrices. This matrix here plays the role of 0 there. Or among the 2 by 2 matrices, this is the 0 matrix. And the matrix that plays the role of 1 is a square matrix. For example, if it's a 3 by 3 matrix, it's a square matrix where you have zeros everywhere else, but you have 1 on the main diagonal. So this matrix is called the identity matrix, and we are denoting that by I3. So 3 indicates that this is the identity matrix among all the 3 by 3 matrices. So next we're going to talk about these matrices, the 0 matrix and the identity matrix. A matrix whose entries are all zeros is called a 0 matrix. We will denote a 0 matrix with an uppercase O. So whenever you see an uppercase O, that's the 0 matrix. Properties of the 0 matrices. So in these parts of this theorem, think of C as a scalar. And if the sizes of the matrices are such that the operations can be performed, then we have matrix A plus the 0 matrix, or the 0 matrix plus A is going to be A. Matrix A minus the 0 matrix is going to be A. If you add up matrix A and the negative of matrix A, or if you just do A minus A, you're going to get the 0 matrix. If you multiply the number 0 by any matrix, you're going to get the 0 matrix. I think that's clear because you have to multiply that 0 by every entry. You get the 0 for every entry. And finally, you have something that's very similar to the 0 factor property. So I'm going to remind you the 0 factor property of real numbers. And then hopefully you will see how this part here, E, is similar to that. for real numbers, we have this. If you have A times B is 0, then the conclusion is either A is 0 or B is 0. Because if none of them is 0, then the product cannot be 0. So if you see that A times B is 0, then for sure either A is 0 or B is 0 or both. So that's called the zero factor property. For matrices, it's like this. If you have a scalar C times a matrix A, and the result is the zero matrix. So you have a constant, or you have a scalar C and a matrix A. And when you multiply them, you get 0. That would only be possible if either C is the number 0 or A is the matrix 0. Make sense? Any questions? Okay. Now, there are two laws that do not work for matrices. I want to emphasize those two. We have seen only one property that doesn't work for matrices so far. We saw that AB is not equal BA. Yes, so that we saw. The next thing I want to look at is the cancellation law does not work for matrices, and the zero factor property does not work with two matrices. So if you have a scalar and a matrix, you have this, so that is okay. But with two matrices, it doesn't work. So let me explain that. So we have already seen in example 1 that the commutative property of real multiplication fails in matrices. So AB is not equal BA. In other words, in matrix multiplication, order matters. It matters in what order you multiply matrices. Two other properties that fail for matrices are the cancellation law and the zero factor property. So this one here, as I said, it's similar to the zero factor property. It's not the exact same thing because C is a scalar and A is a matrix. And here I have reminded you of these two properties. The cancellation law says if you have two numbers, AB is equal the product of two numbers, AC. As long as A is not 0, you can just cancel that from both sides of this equation. Yeah, so as long as A is not 0, you can divide both sides of this equation by A. So you would do AB over A is equal AC over A, and then cancel the A's. You get B is equal C. So that you do not have for matrices. So if you have matrix A times matrix B is equal matrix A times matrix C, this does not imply that B is equal C. You cannot cancel matrices from both sides of an equation. So that's one thing. What about the zero factor property, which I just mentioned? If AB is 0, that implies that either A is 0 or B is 0. That doesn't work with matrices. If AB, and notice that here A and B are both matrices, is equal to 0 matrix, that does not imply that either A is the 0 matrix or B is the 0 matrix. That's the 0 matrix. Is that clear? So do not confuse these two. If you have a scalar times A, and that is equal to 0 matrix, that one implies that either C is the number 0 or A is the matrix 0. However, if you have AB is equal 0, that does not imply that A is 0 or B is the 0 matrix. And the other one is cancellation. AB times AC does not imply that B is equal C. Okay, so these are the laws that fail. So this means it does not imply. In order to prove them, we just need an example. And here you have the examples. So in order to actually disprove something, you just use an example. You cannot prove something with an example, but in order to disprove something, you can just use an example. And here are some examples. So you can check with these three matrices, A, B, and C. If you multiply them, A times B or A times C, you'll get the same answer, 3, 4, 6, 8. However, clearly, B is not equal C. B is not equal C. So the fact that AB is equal AC does not imply that B and C are the same. You cannot cancel the A from both sides of this equation and say, okay, then B and C are the same, because they're clearly not. Is that clear? Do we all understand the purpose of this example? Here we are trying to show the failure of the cancellation law. And when you are trying to prove something does not imply something else, the only thing you need to do is an example. So I found three matrices A, B, and C, so that AB is 3, 4, 6, 8. A times C is the same thing. However, I cannot cancel the A's because B and C are clearly not the same. You good? Okay. Next example, this is the failure of the zero factor property. Here I'm using two matrices A and B, which are not zero matrices. This is not the zero matrix. This is not the zero matrix. None of them are zero. But if you multiply them, you will see that the result is going to be zero. So what does this show? It shows that the product AB equals 0 does not imply that either A is 0 or B is 0. Maybe none of them is 0, but the product is 0. And in this case, none of them is 0, but the product is 0. You're good? Okay. So next we talk about the identity matrix. So as I said, the identity matrix plays the role of 1 among matrices. This is I2, the 2 by 2 identity matrix, I3, the 3 by 3 identity matrix, I4, the 4 by 4 identity matrix. You have zeros everywhere else but ones on the main diagonal. So just as the zero matrix plays the role of the real number 0 among matrices, the identity matrix plays the role of 1. For example, if you have this matrix, which is a 2 by 3 matrix, let's say A is 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3. If I multiply A by I2 from the left, which will be defined, or if I multiply A by I3 from the right, in both cases, I'm going to get A. So multiplying A by I2 from the left, which is defined, or multiplying A by I3 from the right, which is also defined, is not going to change A. So generally, if A is, let's say, M by N, if I multiply IM by A, or if I multiply A by IN, I'm going to get A. Any questions? Okay.
So the order doesn't matter if the I is
The order in multiplication definitely matters, but I'm not multiplying by the same thing. If A is M by N, yes, then I can multiply by the identity matrix of size M from the left. But if I do this, that would be undefined. You see that? Because look, A is M by N, and IM is M by M. You see, they're not the same. So this would be undefined. However, this one is defined. This one is also defined. And it's as if you're multiplying by 1. You get A. Make sense?
Yeah.
Okay. So, theorem. If R is the reduced row echelon form of a square matrix, n by n matrix, then either R has a row of zeros or R is the identity matrix. Very interesting theorem. So let's try to understand this first. This one is saying that imagine you have a square matrix that's 3 by 3. And you do some row operations and you try to transform that into reduced row echelon form. Then only there are two things that can happen. Either this is I, in this case going to be I3 because it's 3 by 3, or there is a row of zeros. There is a row of zeros at the bottom, or 2 rows of zeros at the bottom. So that's what the theorem says. It says if R, so this matrix R, if it is the reduced row echelon form of a square matrix, that's n by n, then either R has a row of zeros, at least a row of 0, maybe 2 rows of zeros, but at least 1, or R is the identity matrix. So when you do these row operations and you go from the original matrix towards your reduced row echelon form, either you get the identity. If you don't get the identity, then you definitely have a row of zeros. Proof? If R doesn't have a row of zeros, then what does that mean? If it doesn't have a row of zeros, that means every row has a leading 1, right? If R does not have a row of zeros, then every row begins with a leading 1. So that means we have exactly n leading 1s. So for a 3 by 3 matrix, if there is no row of zeros, that means there are 3 leading 1s. Because every row must begin with a leading 1. And we know in the reduced row echelon form, you cannot have any number other than 0 above or below the leading 1s. That will automatically make this the identity, because you have 3 leading 1s. The leading 1s, they have to form a staircase. So the leading 1 further down must be further to the right. And also there must be zeros above and below the leading 1s. So if you have 3 leading 1s, then it's the identity. So I'm going to read the proof again. If R does not have a row of zeros, then every row begins with a leading 1. Thus, we have n leading 1s. Since we cannot have more than 1 leading 1 per column because of the echelon form, then every column has a leading 1. If every column has a leading 1, then automatically everything other than that leading 1 in that column must be 0, that makes R the identity matrix. And if you have a row of zeros, then there is no argument. Then you have a row of zeros. So only two things can happen. You either have a row of zero, but if you don't have a row of zero, it's the identity. Make sense?
Yep.
Great. What really matters for me is you understand the theorem. Yes. So if you are struggling with the proof, no problem. You can think about it more. But what I really want you to understand here is what the theorem is saying. It is saying that for a square matrix, only two possibilities. If you are reducing it, if you're transforming it to the reduced row echelon form, either you get the identity. If you don't get the identity, you definitely get at least one row of zeros. Okay. Next thing we're going to talk about is the inverse of a matrix. We know all numbers have inverses except for the number 0. So what is the inverse of 2? 1 over 2. Why is 1 over 2 the inverse of 2? Because if you multiply them, you get 1. 2 over 3, what is the inverse of that? 3 over 2. Because if you multiply them, you get 1. Negative 2 over 7, the inverse would be negative 7 over 2. Because when you multiply them, you get 1. 5, what is the inverse of 5? 1 over 5. Because if you multiply them, you get 1. The only number that is not invertible is 0. What is the number so that I multiply by 0 and I get 1? Such number does not exist. There is no number that I can multiply by 0 and get 1. So that makes 0 uninvertible. It's not invertible. We have almost same story for matrices. There are some matrices where you can find another matrix like B so that A times B or B times A is the identity matrix. In that case, you would say that A and B are inverses of each other. And there are some matrices, let's say C, where it is impossible to find a matrix so that if you multiply that matrix by C, you get identity. So this matrix does not exist. In that case, you would say C is not invertible. So what is the definition of the inverse of a matrix? We know that for every non-zero number A, there exists a real number 1 over A such that when you multiply them, you get 1. And 1 over A can also be denoted as A to the power of negative 1. It's called the inverse of A. It's also called the reciprocal of A. Now, definition for matrices. If A is a square matrix, and don't forget that inverses are only defined for square matrices. So if you have a matrix that is not square, if it's, for example, 2 by 3, then we don't talk about the inverse of a matrix that is not a square. Only square matrices have inverses. So if A is a square matrix, and if the same size matrix B can be found so that AB is identity, BA is also identity, then A is said to be invertible, or it's non-singular, and B is called to be the inverse of A. And then because this definition is symmetric, I hope you realize that then automatically A is the inverse of B. If such matrices B cannot be found, then A is said to be singular. So matrices are either invertible or singular. And whether a matrix is invertible or singular depends on whether I can find a matrix B so that AB is I and BA is I or not. If this B can be found, then the matrix is invertible. But if this matrix B, if such matrix does not exist, so that AB times BA, AB and BA are identity, then you would say that this matrix is singular. I cannot find an inverse for that. Make sense? So when you look at this definition, I hope you realize, because of the symmetry that is in this definition, if A is the inverse of B, then automatically B would be the inverse of A. Okay. So we want to verify that these two matrices are inverses of each other. So we are given two matrices, A, which is 2 minus 5, negative 1, 3, and another matrix B, which is 3, 5, 1, 2. It says verify that these are inverses of each other. What do we have to do? Calculate AB, calculate BA, and make sure that in both cases you get I2. And you can do that. You will see that these matrices are the inverses of each other. Actually, I'm going to give you a few minutes to do that. Just, I think 5 minutes would be enough. Multiply these matrices, make sure that you get the identity. And if you get the identity, that would be proof that these two are inverses of each other. 5 minutes.
Sir?
Yep.
Does that mean that A times B equals B times 8 in this case?
Yes, right. So don't forget that we say AB is generally not equal BA. It doesn't mean that you cannot find examples where this is the case. Yes, so we just say that necessarily AB is not equal BA. But yeah, for these two matrices, AB and BA are going to be the same. You see the difference?
Thank you. Yeah.
Yeah, there are, what we are saying here is that in general, if I just randomly write down two matrices, I'm not going to get AB equal BA. I would be very, very lucky if I just write down a matrix or two matrices and then I get AB is equal BA. If I just randomly use numbers and write A and then write B, I would see that AB is not equal BA.
Okay, thank you.
Sure.
Sir, so the only way to know if AB are inverse of each other is by verifying?
So far, yes.
Okay.
I will give you a formula for the inverse of a 2 by 2 matrix, A, B, C, D. We're going to look at the formula for the inverse of that today. But for now, that's the only way of checking it. That means you have to compare that with the definition. What does the definition say? The definition says that if they are inverses, then their product in either way should be the identity. So that's something that we have to check. Okay, did you check that?
Yep.
So good. So you saw that in any order, if I do A times B or B times A, I'm get identity. So that makes these two inverses of each other. So something else that I want you to do is I'm going to give you a matrix and I want you to find the inverse using whatever we learned about solving a linear system. So I give you a hint and then I will ask you to find the inverse of the matrix. So let's say we have 2, 4, 1, 7, something like that. And for this matrix, I want to find the inverse. So I'm going to use the definition. If a matrix, let's say the matrix with unknowns W, X, Y, and Z. If this matrix is the inverse of the given matrix A, then if I multiply them, I'm supposed to get the identity, right? So this is the question. Find the inverse of matrix A, where matrix A is 2, 7, 1, 4. And so far, I have not given you a formula how to find the inverse of a matrix, but you have the definition. If the unknown matrix B with the entries W, X, Y, and Z, if it is the inverse of matrix A, then we should have this matrix equation, right? But this matrix equation can be written like a linear system. It's like this. So this entry here, there are 4 entries. This entry here is going to be 2w plus 7y. Yeah, so 2w plus 7y. The next entry is going to be 2x plus 7z. The next entry would be w plus 4y, and the last entry is going to be x plus 4y. Sorry, x plus 4z. So that means 2w plus 7y is supposed to be 1. 2x plus 7z is supposed to be 0. This is supposed to be 1, 0. And then w plus 4y is supposed to be 0. And x plus 4z should be 1. Isn't that a linear system? 4 equations, 4 unknowns, right? So everybody work on this problem. Try to find the inverse of the matrix A. I'm going to give you 10 minutes for this.
Sir?
Yes.
I think I found the answers. Are you gonna explain I just want to make sure I got the right answers. Are you gonna
Yeah, the
explain?
answer is this. You're gonna get 4, -7, -1, 2.
Okay, perfect.
So what about the rest of you? You got the answer? Do you want me to do it or you got the answer?
Can you do it, please?
Okay. So if I write down the augmented matrix, I need one column for W, one for X, one for Y, one for Z. So it's going to be 2, 0, 7, 0, 1. Then for the next row, I get 0, 2, 0, 7, 0. Then I get 1, 0, 4, 0, 0. The last row becomes 0, 1, 0, 4, 1. So if you write down the augmented matrix, I think the rest is going to be easy. Do you understand how I got this augmented matrix?
Yeah.
Okay. So actually, in order to get a leading 1, I'm going to swap row 3 and row 1. So I get 1, 0, 4, 0, 0, 0, 2, 0, 7, 0, 2, 0, 7, 0, 1, 0, 1, 0, 4, 1. Then I'm going to do row 3 minus 2 row 1. 1, 0, 4, 0, 0, 0, 2, 0, 7, 0, 0, 0. Negative 2 times this added to this negative 1, 0, 1, 0, 1, 0, 4, 1. Okay, next I need a leading 1 here, so I'm gonna swap row 2 and row 1. Sorry, row 2 and row 4. 1, 0, 4, 0, 0, 0, 1, 0, 4, 1. Row 3 doesn't change. 0, 0, negative 1, 0, 1, 0, 2, 0, 7, 0. Next, I'm going to get a 0 here. So for that, I will do row 2, row 4, minus 2, row 2. 1, 0, 4, 0, 0, 0, 1, 0, 4, 1, 0, 0, negative 1, 0, 1, and then 0, negative 2 times this added to this 0, negative 2 times this to this 0, no change, and negative 2 times this is negative 8 added to this negative 1, and negative 2 times this is negative 2 added to this negative 2. Make sense? Okay, I'm gonna take a snapshot of this. Next, I will need a 1 here and a 1 here, and also zeros above that. So what I'm gonna do is I'm gonna get zeros above first by doing row 1 minus or plus 4 times row 3 and row 2 plus 4 times row 4. So if I do these two operations, I'm going to get zeros above those positions here, which is going to be my leading ones after. So I'm going to get 1, 0, 0, 0, and then 4 times this added to this, it's going to give me 4 here. Four times the last row added to the second row, I get 0, 1, 0, 0. And then 4 times -2 is going to give me -8. And for the last two rows, at this point, I'm going to multiply by a -1. So I get 0, 0, 1, 0, -1, 0, 0, 0, 1, 2. That gives me the answer. Yes? 4, -8, -1, 2. Yes? And so I erased that, but can you remind me what the original matrix was? A? I think it was 2, 4,
7.
Here was 7?
Yeah, and then the other one is 1.
1. Okay, so 2, 4, 7, 1, 4, 2, -1. I'm supposed to get a -7 here. So what mistake did I make? When I'm adding 4 times this to this. So four times row 3 added to this. Oh, I have a 7 here. Four times this added to -2 times this to this one. Okay, see that. Let's go down. Looking at the wrong matrix. 4 times this to this. 4 times this, this 4. Then, yeah, that's it. You see, when I do 4 times this, I get -8 added to this gives me -7. So that was my mistake here. So, yeah. Then this is supposed to be -7. That's the answer. Now I'll give you the formula. So, and you'll see that this formula is going to be much easier than what we did here. If you have a matrix A, and it's A, B, C, D, yes, then you calculate something called the determinant. You're going to talk about determinant a lot later on. It's actually the material for one whole chapter. The determinant in this case, for a 2 by 2 matrix, which I'm going to denote with determinant of A, is going to be AD minus BC. So these two, multiply them, minus the product of these two. So AD minus BC. If this is not 0, if this determinant is not 0, then there exists an inverse for this matrix. And that inverse, which we're going to denote with A inverse of A, is going to be 1 over the determinant AD minus BC times the matrix. And for this matrix, you swap A and D. So D goes here, A goes here, and you negate B and C. So that's how I knew the answer. I multiplied the 2 and the 4, 8 minus 1 times 7. So I got determinant of A is 8 minus 7, it's 1, and 1 is not 0. So I was sure that this matrix is invertible, so the inverse exists. Then I use this formula. I'm going to get 1 over 1 times, I have to swap 4 and 2. So 4 goes here, 2 goes here. Negate the 7 and the 1. So -1, -7. And then I do the multiplication. 1 times this is going to be the same thing.